All right, folks, it's Bass Action, back in action here. In this video, we're going to go through our last of the special segments and points of concurrency. And our last segment is called the altitude. And although we're not going to necessarily do a ton with this semester, it's a really significant special segment second semester when we're working with area. So let's jump into its definition and how we can use it and some things that we might work with it this year. So an altitude is also actually called the height of the triangle, okay? Now you guys know height from your area of your triangle, that is going to be 1/2 base times height, okay? So the height of the triangle, the altitude, is a pretty significant segment for us. Now, by definition, an altitude is going to be a line that is going to pass through a vertex and is going to be perpendicular to the opposite side. So far we've had 3 types of segments that always pass through the vertex, and that's our angle bisector, our median, and now the altitude. Remember, the perpendicular bisector does not necessarily go through a vertex. However, the altitude is perpendicular, and that perpendicular bisector is also perpendicular. So we'll have 2 segments that are always perpendicular, and we'll have 3 segments that will always go through the vertex. Now, when we look at these 3 pictures here, just like all of the other videos and all the figures in the other videos, these have been perfectly constructed to truly represent an altitude. So what we can do is we can go through, since we know it's going to go from a vertex and be perpendicular to the side, we can go ahead and we can start identifying these different altitudes. So there's one of my altitudes, then I'm going to have another altitude, and then I'll have my last altitude is going to be right here, and we can highlight that one as well. And we're going to come over here to our right triangle. So if this is a nice right triangle, your right angle might already be filled in. If this is our right triangle, we're going from a vertex and being perpendicular to a side. So we're going to have a right angle here, and we can highlight that nice altitude. Then the tricky, interesting thing about a right triangle is if I go from a vertex to the other side, notice that this leg here is in fact also an altitude, and this other leg is going to be an altitude. So that's pretty significant for us. And then on our last one, our obtuse triangle, you'll notice that this point of concurrency is outside the triangle. We've seen this before with our perpendicular bisectors, the orthocenter, or the circumcenter. And what we're going to do here is we're going to kind of extend this side here of the triangle so that we can get that perpendicular. So the altitude is going to be just this piece right here. Now, if I extend this other side right here, it's sometimes a little tricky, so we're going to extend this side right here. So it just like is extending that out. Mine's a little bit crooked. Then what we're going to find is that we're going to get a right angle right here. And I'm going to highlight. So its altitude is that piece right there. And then our last altitude is going to be this piece right here. And we'll put its right angle right there. So its point of concurrency is way out here. So it's in the opposite direction of that circumcenter that we had before. So its point of concurrency is going to be called the orthocenter. And just as I just mentioned, that in a right triangle, the legs of the right triangle are also altitudes. And the orthocenter, we can see if we look at that right triangle, is actually on the right angle. It is that right angle. So our orthocenter is right here. So with the circumcenter, it was the midpoint of the hypotenuse. The orthocenter can be the right angle itself. Okay. Now let's look at some problems that we can do with this. Now, if I've got a nice right triangle here and I'm telling you that WB is an altitude, so the first thing that we want to do is we want to label that nice right angle. Notice that we can't label anything other than the right angle there. Now, we're going to look at all the things that we could do with this particular figure. So I'm going to tell you that AB is going to be 3 units. I'm going to tell you that AC is going to be 5 units. And since the triangle is a right triangle, we will be able to easily do a Pythagorean theorem for our last side. Let's first look at this question A, identify the orthocenter. So the orthocenter for this problem, since it's a right triangle, is going to be this vertex B, just that point B, and then the other altitudes will be those legs AB and CB. It's really important that you start to recognize those. Now, let's go ahead and use our Pythagorean theorem to find this missing side for B. So just a really easy Pythagorean theorem here. You might even have this Pythagorean triple memorized. So we're going to have 25 equals 9 plus x squared. So my x squared is going to be 16. So BC is going to be 4 units. And we can come over here and even put that back on our picture for us. Now, if we want to find the area of the triangle, we've actually done this before. If we want to find the area of the triangle, we know that if it's a right triangle, we can simply use the legs of a right triangle to find the area. So our area of this triangle is going to be 1/2, 3 times 4. So our area is going to be 6 units squared. Now, this is where it gets really, really important for us, and you've got to start to really think outside the box. If we want to find the length of WB, we don't have enough information to be able to do a Pythagorean theorem here or a Pythagorean theorem here because we don't know how this 5 has been divided between the two pieces. Remember, W is not necessarily a midpoint. But what we can do is recognize that the area of a triangle can be calculated anytime we want using these altitudes. So I can take the fact that we just did 1/2 and we did AB times BC, and that should equal the area of the triangle from a different perspective. And that's going to equal 1/2. And it's going to be my base of AC, that of course I know what it is, and WB that I'm looking to find. Now, we already found 1/2 AB times BC. We did it right here. So we can fill this piece in as 6, and then 1/2. We know that AC is 5. We're just working from our picture. And WB, we don't know what it is, so I'm going to fill in a new variable of y. So now, if I continue solving this, I'm going to get a 12 equals a 5y, so y is going to equal 12 over 5. And we do not want to convert this to a decimal. We want to leave that as that nice 12/5. Now, using that, if I come back here and I'm going to fill in this, oops, that's not the part I wanted, I'm going to fill in this piece as 12/5, because now what we're going to do is we're going to find the length of AW right here, okay? So I'm going to call this a new variable. I'm going to call this Z. And now we're going to do our Pythagorean theorem again, and we're going to work with this little triangle right here, and we're going to work with these fractions. And we can do this, okay? So we're going to take the hypotenuse of that little squiggled triangle, and that's going to be 3, so we're going to fill that in nicely here as a 9. And then one of the legs we know is 12/5. I'm going to square that, and that's going to equal, or add that to, sorry, Z squared. Now, I have to remember to square the top and the bottom. So if I'm solving for Z squared, I'm going to square this, and I'm going to subtract it. So this is going to become 9 minus 144 over 25 equals Z squared. And I know this looks pretty overwhelming right now, but it's actually going to clean up and turn out pretty simple here in a second. So we're going to get common denominators. I'm going to put that over 1. I'm going to multiply 25 over 25. That's going to give me my 25 times 9 minus 144. We poke that into just our simple calculator. That's going to give us an 81 over a denominator of 25. That equals Z squared. Now, I'm going to take the square root, the square root, and the square root. So my answer for Z turns out to be simply 9 over 5. Now, you would not get that very cleanly if you tried to convert this to decimals, so definitely don't convert to decimals. Okay, the last thing that I'm going to do is we're going to look at some coordinate geometry. Now you probably need to pause the video because I've already done a few things for us. I've gone ahead and I've plotted the points of our triangle. You'll recognize these numbers as the same ones that we used for our coordinate geometry before when we worked with our circumcenter. I've plotted the points, and if we want to find the orthocenter algebraically using coordinate geometry, what we're going to need to do is we're going to need the equation for two different altitudes. So I've chosen for you, I'm going to go from A to my side BC. Okay, so I'm going to go from A to BC, and I'm going to go from my C to my side AB. So I always like to write this out first. Now, my altitude should go from A, so you can see I wrote that ordered pair, to BC. So I'm going to need to start with the slope of BC. So my slope of BC, I've calculated, you should be able to calculate it too, is 1, which means my perpendicular slope is going to be -1, which means I can now write the equation for my line and say y minus 1 equals -1 and x plus 2. This one cleans up pretty nicely to give me a -x minus 1. Over here, I know I'm going to do from C to side AB. So I've got my point C. I want to call your attention to notice that this point is in fact a y-intercept. This is going to make our life really, really easy when we go to write our equation for our line. I've also calculated my slope of AB right here. You guys already know how to do slope. We've been doing it for a while. So my perpendicular slope is going to be a -3. So now I know my point needs to, my y-intercept is going to be 0, -3. My slope is -3. That's a nice coincidence. So my equation is a -3x for my slope minus my y-intercept. Now, I'm going to set these two equal to each other. We've been here before. We've done this so many times. I'm going to take my first equation. I'm going to set that equal to my second equation. And now I'm going to just start solving, okay? So I'm going to move the -3x over, and I'm going to get a nice 2x. I'm going to move the 1 over. I'm going to get a nice -2. So my x value is going to be a -1. I'm going to substitute that back in. I like to substitute into this one. So a negative of a -1 is going to be a +1. -1 is going to be 0. So my orthocenter is a -1, 0. Now, the last thing that I'm going to do is I'm going to go ahead and I'm going to plot this point. Now, your graph probably looks a little better than mine because it's not on an iPad and easier for you to draw straight lines. But what I want you to notice is that we can actually sketch in these altitudes. So remember, I'm going from C to AB, so my slope is -3. So from C, I'm going to go 1, 2, 3, and I'm going to go over 1. So that's going to create this altitude. And notice it's perfectly passing through that point that I just made as my orthocenter. My other altitude is going to go from A, and it's going to go to B, and its slope is going to be a -1. So I'm going to go down 1 over 1. And when I go down 1 over 1, down 1 over 1, I sure enough still also pass through that beautiful orthocenter that I already calculated. And these do in fact look like nice right angles. Okay, so that's the last thing that we've got. That's our last of our special segments, and we're going to work to put those all together and practice more coordinate geometry in class.